Greetings, welcome to this demonstration. It's a demonstration of a NanoEdge AI Studio anomaly detection model that you add to a STM32 Cube IDE project for embedded firmware, and I'm using a H7 board. So I have this checked into my GitHub, but it's only going to work if you have that board. But this just shows you the experience of it without having physical sensors, without having a board with actual physical sensors. Now, if you want a more realistic demonstration or a realistic experience, you'll need to get a board like this B-U585I- is that an I or a 1 or 1OT02A discovery kit. And I have a link to the documentation for that and to a YouTube video tutorial. So here are those resources. So you can get the NanoEdge AI Studio, which I'm not going to go into too much. I'll just walk you through it pretty quickly. The reason I'm not going to go into it too deeply is because I have my board and I kind of cobbled together some signal data based off of the TensorFlow anomaly detection, and you're going to get a different result, and I provide you with some inference data that will work with this particular library if you have my board. Otherwise, the demo's not going to work. So it's a limited scope, kind of works on my machine in a way, but you'll need to have an H7 or at least a Nucleo 144. It might work with any one of those, although I've only validated it on my board. Then here's a link to the documentation for using the NanoEdge AI Studio, and then the video from ST Electronics on YouTube. And then this is my GitHub, and on the last slide I have links to the project itself that I've checked in. So the goal is to demonstrate the pipeline of how you create the model, or it actually comes in the form of a static library and a couple headers. And it's kind of a pseudo scenario where there's no physical sensor input. We're just using floating point data, basically, that I've sort of based upon a subset of the TensorFlow tutorial, which I have a link to that too, like I said on the last page. It takes some patterned signal files that it feeds to do a search of NanoEdge maintains a catalog of algorithms, and so it does a search based on the board that you're targeting and the data that you're providing it to come up with a model or algorithm that best suits your configuration. And so I use a ST link over USB. And then also I'll show you how to copy over the files. Although if you just use if you clone my enlistment, I have the files, the header and the lib, but that lib will only work with my board. So you might try it with your own board, go through the steps, but I can't guarantee any results, and I can't really supply you with any signal data that I know that will work with your board. Also, I have an optional COM port client, but you don't really need it, but it's nice, and my demo will show you that. And I have that COM client zipped up in my enlistment. So the way I started it was to go through the TensorFlow tutorial, and they give you a script that you train it with. And so what I did was to make it a little bit more interesting, as I created the model. It's a Keras format, and then I wrapped it in a Flask server. So that's running right now, this Flask server, and it's waiting for HTTP JSON requests. And so over here in this other console on the same machine, so I'll run it, and what it does, it has one regular signal or regular data. The format is 140 floats, and so and then another one that has an anomaly. And so here's the output. So the first one is regular because anomaly is false, and the second one has an anomaly and it's true. And then the Flash server posts the results up to this website. So it's a web server too. And there's 4 entries because I tested it before I started the video. So these are the last 2 entries, and these were the ones that I tested to make sure that I was ready for the demo. And so I provide a link to this TensorFlow tutorial. It's autoencoders. And so the third example is anomaly detection. So they have you download this CSV file doing a pd.read_cvs. I'll show you the format of that. Well, here it is right here. Here's the format of it. Here, let me make this bigger. So they're floating points, and there are 140 columns, and then it can be as many rows as you want. So here's the raw data, and so you get these 140 floats, but the very last, there's a 141st column. This one says 0.0, and there's others that say 1.0, and that is the classification of each one of these rows. 0.0 meaning regular, that there's no anomaly, or that you wouldn't expect one. At least they say it wouldn't expect one. 1.0 means they would expect an anomaly. But what I have found is that when I created the model and trained it, that there was quite a bit of overlap. And so I did let the model tell me which ones were anomaly and which ones were regular. I don't know if that's a flaw in my model or a flaw in how they created this data. You mean, think if it's from TensorFlow, it'd be golden, but that's what I did to set the threshold that the model was performing on. And basically, I took all the results of these rows that overlapped, with the anomalies with regular, the overlap, and sorted them, and then just found the midpoint by count and moved each one into the anomaly or regular category. And then the highest number, I found the ideal threshold right there by the result of that middle record. But anyway, that's what I did to get it to work. For this, like I say, it doesn't have sensors, and it's just this is a demo that's based off of this TensorFlow tutorial. And so my result, the NanoEdge Studio wants you to provide them with regular signals and anomaly signals, and they want it to be space delineated. And so you'll have to convert those if you want to do it. But so what I did is I let the model decide on those overlapped ones and put them into either the anomaly file or the regular file. And so there's 2 sets of data. And so I use these anomaly and regular.csvs to open from my client so that I can feed the model from my COM port, or you don't have to run it that way. I have 2 modes. Well, I'll get to that later of running the demo. So it might make more sense if I walk you through the NanoEdge AI Studio. So you can create a new project. Detect anomalies is the one that I chose. Here's one I did with the board I'm talking about. So here's the steps up here at the top: project settings, signals, benchmark, validation, and deployment. So if you look at the signals, you see that I've added these space delimited signal files. And so this is what they look like. There's 140 columns, 140 floats, but you take off the last label, they're called, the 1.0 and the 0.0, because you know that this particular one is normal. And so this is the one you're going to add to add signal. So you're going to add here. I'll open that one up. I won't save it though. So yeah, here we go. Normal. Show you what it looks like. So if you look here, here's the format of it, and it likes it. It gives you the OK. So that's the data. I'm not going to import it. Then you benchmark it, and I already did a benchmark, and here's the results. You add a new benchmark with these two files, and then you say start. I guess I can show you what it looks like. I'll wait till there's a little more action. I'll pause the video. Okay, so it starts giving its best library performance. Well, right now it's only at 5%, so but it's already jumped up to 77 points and 80% balance accuracy. And by the time this is over, both of these are going to be close to 100%. And then you'll have, let's see, can I stop this? Pause. Okay. What happened is, this is from the last one I ran, or is this just from right now? Anyway, you can see that, yeah, no, this is from the one we're just running. So when it's finished, there'll be a lot higher percentages and points, so to speak. And you'll choose the one based on the best balance, accuracy, and quality index, and then minimal iteration for training, and your flash and your RAM sizes and so on. And then you'll deploy it, and you want to click this knowledge button, and what it gives you is gives you a zip file. And I have some of these already. I'll open one up. So when you extract that zip file, it gives you some it gives you two headers that you're going to put in your STM32 Cube IDE project and this library. And it gives you an emulator if you want to check on some of its attributes and so on. But anyway, these are the three files that you bring over, and you put the two headers in your inc core/inc. And then my project, I made a core/lib, and you add that to your lib folder, then go into project settings, and I'll show you how to do that. So you go to properties, and then you go to C++ general, and then to path and symbols, and there's these tabs here. And so first one is library path, and I've added core/lib, and then there's libraries, and you add it. Now in the file name that you get in the zip file, it's called lib.neai.a, but you just put in neai, and that's it. Okay, so I've just covered showing you sort of how I've based this off of the TensorFlow Keras model and the CSV file that you download from them. I'm using a subset that I use as sensor input in the NanoEdge. Did the benchmark, validate, selected a lib, deployed with knowledge. I copied over those two headers in the lib file and set the project settings like I showed you. And now there's code that you call, init and detect and knowledge. I'll show you that in the code. So first of all, you add the two headers, NanoEdge AI.h and knowledge.h. Knowledge.h just has some floating point data that helps determine the inference. It's the training data in compact form. So then after I've initialized all my peripherals, and I'm only using UART for this one, here's the calls. Actually, I'll show you the APIs in that header, NanoEdge AI.h. We have some constants here that you can use, the buffer size, the access number, that means how many rows. Now I put in this data rows 10. I put it in this header, so that's something you'll have to add that, and that's the only thing you add to this file. And here's the APIs you can call. You got to call anomaly detection _init before you can, and then you can call learn, but I'm using knowledge, and so I load in the knowledge. I load in this knowledge array instead of training it. Now, supposedly you can add training and it doesn't override the training that it had, but this works well, so I'm not messing with it. So you see, I start with the init, and then I load the knowledge. And then I just set up my, now this, like I said, there's two modes. If you don't want to mess with my COM client, you can just run it. And I have this inference function that after you've done the init and after you've loaded the knowledge, I have some data here locally on the machine right here. So here's my normal data rows. There's 6 rows, and then there's 6 rows of anomaly data. And this inference call just iterates through these loops and gives you the result, and it prints it out. And so you have to use your PuTTY or a terminal in here to look at the results through the COM port that your board uses. So to turn that on, you just uncomment out this call to inference like that. But I use my own COM port reader that's included in the zip file in the project, and I interact with this model through the sending stuff. So I have an interrupt handler that uses this RX event callback, and what's nice about that, instead of just HAL UART receive, is that you get this size parameter. And so what you do is you may not get, have this client that sends 140 floats, and you're going to receive it though as uints, and that's going to be 560 uints that you're going to have to pack into 140 floats. And so I have this Python app that sends it as binary data. And so what I have to do is, until I get the entire 140 floats through the UART receiving pipeline, I have to just keep populating this floating point array that I'm going to pass to the detection function. That's what it takes. It takes a buffer of 140 floats, just like for training it. And so I just keep rearming the RX UART pipeline until it's full, until it's received 140, and then I go ahead and now I have a fully populated buffer, and I go ahead and call the detection function, and it prints out the results. That's if you want to use the COM client, which I'll show you how that works here. So I have it set at COM port 4. That's the way that you figure that out if you're on Windows. Is you open up the device manager, you go to ports, and here's your ST-Link COM 4, and then you can look at properties. And I use this highest baud rate, 115200, and my project, my embedded firmware matches that baud rate for the USART3. And so I have that set. Before I can do it, so my board is running. We don't need to run the debugger. It's running without the debugger. That firmware is going. So first thing you have to do is you have to start listening. And there it is. It's ready. It's not super fast. So I'll just send one. And I have this control pre-populated with one of the datas. And so there it is. Similarity equal 100. Now 100 means regular. Anything less than 100 we're calling an anomaly. Now the reason I like this COM port is because I can clear it. And so then the other thing you can do is you can send a file. And so this goes right to the local directory of the client. And I can pick up anomaly data. And since we just did regular, you can see what anomaly looks like. And I click and open it. And I pause the video because it takes a few seconds. It takes like 10 seconds round trip. So here's the results. So there were 6 rows of data, and all of them were less than 100. So we're categorizing those as anomaly. So I'm going to upload these slides, or a PDF version of the slide, and gives you sort of the instructions here along with this video. And then the last slide I have, this is the link to the project itself. This is a link to the TensorFlow detection tutorial that I was telling you about. This is about me, my LinkedIn, and this is my YouTube channel, Music and Technology. And I will be uploading that and put a link to that in the GitHub, and put a link to the GitHub in the description of the video. I'll put a lot of this in the description of the video. So I think that's about it. It's been going on for 20 minutes. So that's a good time to stop. So thanks for your attention.